anything that is our body that is soluble in the organic solvent, that is considered a lipid. Okay, so it's a very broad definition for lipids. So fatty acids, as the name suggests, is an acid. So that means that you have a long chain of hydrocarbon. As you can see on this side here, a long chain of hydrocarbons, they attach to a carboxylic acid. That's why it's known as a fatty acid. It's an acid, right? But because of this long hydrocarbon chain, generally it is very hydrophobic, very hydrophobic, even though it has a carboxylic acid in the end, right? So in our body, most of the fatty acids are made up of 16 or 18 carbons. Okay, so you can count from here. It starts from the carbon that is attached to the carboxylic acid, so which is number 1 here. And we count the carbon. Generally, you have 16 or 18 in our body, but there are also others which you can get from dietary as well. So how do you remember? You will have to remember somehow. If it's 16 carbon, it is known as nucleic acid. Alright. Whereas if it's a carbon 18, which means that if you have 18 carbon instead, it will depend on whether the carbon chain is fully saturated or there is a saturated bond inside. So you know what saturated and unsaturated is, right? So when you talk about saturated means it's only sp3, so that means all are single bond. But if it's unsaturated, then you will have a double bond inside the chain as well. So depending on how many numbers of double chain, you will have a different name for the fatty acids, right? So for example, if it's C18 without any double bond, it's known as stearic acid. Okay? When you have one double bond, it is known as oleic. Yes, oleic. O-L-E-I-C, oleic. And then if you have two carbons or two double bonds, then it's known as linoleic. If you have three, then it's known as linolenic. Okay, so that's how you differentiate them. So if you notice, right, for the double bond, usually the double bond is actually at the 9th position in the bond. It actually starts at the 9th position, right? Regardless of whether it's oleic acid, linolenic acid, or linoleic acid, generally the double bond will start as number 9, carbon number 9, and then the subsequent double bonds usually is 3 bonds apart. And I repeat it. So generally the second double bond or the subsequent double bond usually is at 3 bonds apart. So if the first one is number 9, the second double bond starts at the shell. Okay? And because it's separated by 3 carbons, it is not conjugated. I'm not sure whether you're familiar with conjugation. So conjugation is when you have a double bond, single bond, double bond, single bond, right? But in this case, the fatty acids, generally the double bond is separated by 3 carbons, so they are not conjugated. Okay? So that's the difference. That's the uniqueness of the fatty acid. And there's a reason for that. You'll learn that in your lipid metabolism lecture. Okay. And most of the time in our body, right, most of the fatty acids are generally unsaturated. You need to say they will somehow have some double bonds inside the fatty acid chain. And the double bond always exists as a cis conformation. So you can see here, cis means that what? The H is on the same side, right? It depends on how you see it. You can see whether the substitution is at the same side or the H is at the same side. It's the same thing, right? So cis, sorry, there's something flying in front of me. So the cis is always exists as a cis, and because it's existing as a cis, it will actually force the fatty acids to form a 30 degrees band. So you can see that there's a band here, there's a 30 degrees. Okay, so and because of this double bond, right, because it forces the structure, if let's say it's just a linear unsaturated, saturated hydrocarbon, right, which is just a single bond, it will be straight, like what you see here, right? But when you have a double bond, it forces it to actually curve a bit, right? So it becomes a bit bent. So when it becomes a bit bent, just imagine if you have like multiple of these fatty acids lying together. If you have a single straight line packed together, is more, how to say, the packing is actually better, right? Because it's close to each other. But when you have something like, you have a straight chain and then you have something bent, and then you straight chain like that. So obviously the packing is less compared to the one which is just a straight line, right? So the reason of why I'm sharing this is because when there's a slight change in the packing like that, it actually affect the interaction between the chain. So the interaction between the chain will be stronger when the packing is tight, right? It's like if you have a straight chain next to each other, that is a very strong interaction between them. But if you have like a pack between a single chain, a band chain, single chain, band chain, then the interaction between the chain will be lesser. So the interaction is actually weaker, right? So that will actually interfere with its fluidity, right? The term is fluidity. So we need to say if it's weaker, the interaction is weaker between them, then that means it tends to move more fluidity because it's not tightly packed, right? So in other words, the melting point, that is the energy that is required to actually break the bonds apart, is also lesser. Okay, so just take note of that. So that's fatty acids. Any questions? So how can we follow, right? It's very straightforward. Okay, now let's move on to the first part of the lipid that uses the fatty acids inside their structure, right? So the first one is known as triglyceride. So take note, the subsequent three types of lipids that I'm going to share with you generally has the same backbone. So what's the backbone I'm talking about? It's actually the glycerol backbone as shown over here. So what is glycerol? Glycerol is actually a tri-alcohol. It's actually an alcohol with a 3 OH. Okay, so you have a CH2 followed by the OH at each of the CH. Right? So that's glycerol. So there will be 3 OH bound to a carbon chain. That's glycerol. So that will be the backbone for all these 3 subsequent lipids that I'm going to share later. So that's why this is known as triglyceride because it has a triglycerol, which is it's actually a triacyl glycerol, meaning to say all these 3 OH of the glycerol is being esterified with the carboxylic acid of your fatty acids. Can follow? And you know, right, acid and alcohol will form ester, right? Okay, so if you look at the triacyl glycerol, you notice that there's actually this ester group. We call it acyl group. So there's this ester group, okay, attaching or mediating the 2 backbones, which is your glycerol backbone and the different fatty acids. Right? So that's your triglycerides. So this is one example of how a triglyceride looks like. So you'll notice that probably one of the chain, the fatty acid chain, will have a 16 carbon. The other one will probably have an 18 carbon. The third one will have an 18 carbon. So you'll notice that there's one with a double bond. Here there's maybe 2 double bonds maybe. And then there's none double bond here, right? So let's say now I ask you that. So if this is 16 carbon, so what do you call this? 16 carbon fatty acids, what do you call it?
Palmitoic.
Okay, palmitoic acid, right? How about if let's say this is an 18 carbon with 2 double bonds, what do you call it?
Linoleic.
Linoleic acid, right? And if there's 18 carbon and without any double bond?
Stearic.
Stearic acid, okay, good. So that's why if you look at the naming of this this triglycerides, right? You actually name based on which substitution or which position of this fatty acid is substituted. So we name it like, for example, this is 1, 2, and 3. So the 1 we know is palmitoic acid. So when you convert it into triglyceride, you become 1 palmitoyl. So the IC will be replaced by OYL. Right, as you can see here. If you see the OYL, this is referring to this. And then the second one, you know, there is a linoleic acid. So when it's inside this part of the triglyceride, then it's called as linoleol, right? The IC is replaced by OLL. Same thing goes to the 3, stearic acid becomes steroid. And then because this is actually part of the glycerol backbone, so of course at the end of it, you just have to put the glycerol there. Okay, so that's how you name the triglyceride based on the type of fatty acids and the position of the substitution. Okay, so generally in the plant, okay, I'm pretty sure that some of you do cook, right? You cook, right? Do you cook?
No.
Okay, good. So, I know this sounds a bit stupid, but yeah. Okay, so if you cook, you know that you're cooking oil. Cooking oil, most of the time you use what? Canola oil?
Oh yeah.
Any type of palm oil, right? Or kacang or whatever it is. So, generally, your oil is in the form of oil, right? So, why is it so? It's because most of the time, the triglycerides that's inside the plant, inside the oil, is actually unsaturated. Right? So you need to say that you have double bond inside, and it's a cis double bond. So because it has a double bond inside, if you still remember, I did mention when it's a double bond, the packing between the fatty acids when they are together are less tight, right? Because of the kink of the band, right? So the melting point is usually lower. So that's why it exists as a lipid in the room temperature, and that's why you look it as an oil. Okay? In contrast, in our body, or in the animal body or whatever, so most of the fatty acids are highly saturated. Okay? We need to say that it's most likely saturated. So we need to say that there is no double bond inside. So generally, they have a higher melting point because they pack more tightly, and therefore it's quite solid at the room temperature. That's why it's known as fat. So if you look at the animal, usually it's solid, right? The fat is solid. It's not oily, right? So that's the reason why you see the different properties for different fats based on what type of fats. And I'm pretty sure if you go and buy cooking oil, again, cooking oil is a good example, you will always look at something called trans fat inside your pan, right? And why is it so? Because as you know, generally anything that is with double bond is not very stable to oxidation. It tends to be oxidized quite easily when it's exposed to that to something else, maybe aldehyde or maybe oxalic acid, whatever it is, and it can actually give a very pleasant smell. So if you keep your cooking oil for too long, for example, you tend to have very bad smell, right? You get the smell, the cooking oil, the smell will go bad after a while. And the reason is because it gets oxidized by the air. Okay? So one of the reasons, or one of the ways the manufacturer actually do to slow down this degradation process or oxidation process is they actually do this partial dehydrogenation process. Okay, so what they do is that they add hydrogen inside to actually kind of convert some of those this double bond into saturated fat, into saturation, that means from double bond reduced to become single bond. Because we know that single bond, then it becomes more stable. It won't be as easily oxidized as the double bond. But in the process of conversion from the double bond to the single bond, what happens is that some of this double bond is also converted from cis to trans. Right? So this trans fat is known to actually cause a lot of problems in our body. So it tends to give this cardiovascular disease and etc. So that's why if you go and buy this cooking oil, whatever, please go and have a look. What are the trans fat important? Because it's not good for health. So that's the idea, right? Okay, so any questions so far? All good? Okay. So at least if you can't remember anything, just think about cooking oil. Okay, so the next one that I'm going to share the type of lipid will be phospholipid. Right? So as I mentioned, all these three different types of lipid I'm going to share, triglyceride, phospholipid, and sphingolipid, they all share the same backbone, right? Similar backbone in a way. So if you remember, you call that triglyceride has a glycerol backbone. Similarly, for phospholipid, you also have glycerol as well. But one of the OH of the glycerol is actually attached to a phosphate group. Okay, so you can see here. So, okay, so this is your glycerol backbone, right? So maybe if you look carefully, the first one here is still attached to a fatty acids. The second one here is still attached to a fatty acids. But the third one here, the OH is actually attached to a phosphate group. Okay, which is why it's known as phospholipid because it has a phosphate group. Okay, and this phosphate group is not purely phosphate group. There's also an additional head group attached to the phosphate group. So this head group, the X here can vary depending on the types of phospholipid. So it can vary, as the examples can be shown over here. So the X can be ethanolamine, can be choline, can be serine, inositol, glycerol, phosphatidylglycerol, etc. And different head groups will give you a different name of the phospholipid. So for example, if it's ethanolamine, then it's known as phosphatidyl-ethanolamine. So the name of the head group will be there. So choline, then you have phosphatidylcholine, also then known as acetylene. If it's a serine, then it's known as phosphatidylserine, etc., etc. Okay. So that's the difference. The difference between the triglyceride and phospholipid is very simple, just by one substitution. Right? Okay. Now let's move on to another type of phospholipid, which has a slight different structure from the phospholipid I shared earlier on, which is very unique, plasmalogen. Right? Plasmalogen. So this one here, why is it different? Okay, or how is it different? If you look carefully, the OH that's attached to the phosphate group is still there. The second CH that's attached to the fatty acid is also there. But the first CH that was attached to the fatty acids initially in the common phospholipid has been replaced. What is it being replaced to? It's actually being replaced by an ether. Right? Instead of the acyl group, instead of the ester group here, is now an ether group. Right? You know what's ether, right? ROR. Okay, so this is an ether group here, and this ether group is connected to a double bond carbon. And this double bond carbon is still in the cis conformation. Okay, just take note, it's still in the cis conformation, and then only followed by the fatty acids, the R, okay, the side chain of the fatty acid. And so that's the difference between the plasmalogen from the other types of phospholipid. That's the one and only one which is unique. Okay. So again, the name of the plasmalogen is highly dependent on what is the head group attached to it. So the head group can be ethanolamine, choline, or serine, just like what you see for the phospholipid. And what's the function of this plasmalogen? Well, at the moment, the exact function is not yet understood. Perhaps because it has an additional double bond here, so maybe it can actually prevent some free radical damage to other cell constituents. That's what is being proposed, but it has not been proven yet. Okay, so far so good for the phospholipid. Can you follow, right? Okay, good. Very easy as I said. Okay, next one will be sphingolipid. Okay, the name is a bit complicated. But don't worry too much, it's not as complicated as you think. If you look at the sphingolipid, generally sphingolipid has this sphingosine structure, right? Again, it looks very similar to your glycerol backbone, if you notice. So you will still have the backbone here, CH2OH. And then this one here, one of the OH is now replaced by an amino group, NH3+. Okay, that's why it's known as the amino alcohol derivative. Okay, so it has an amino group. And the third one here also has an OH, but one of the H of the third carbon here is now replaced by a trans double bond. Okay, this is the only one with a trans so far. So there's a trans double bond, and followed by the fatty acid side chain. Right? Can you follow? Yes. Oh, you can't find the cursor. Oh, okay. Thanks for telling me that. Maybe I'm using the wrong one. It's supposed to be laser pointer again. Yeah, okay. I probably used the other one just now, so yeah, you should have let me know earlier. So, do I need to repeat the earlier one?
Yes.
Huh? Okay, where should I repeat from? This one? This one? Oh, this one okay, right? This one?
No.
Not okay, right? Okay. So this one here, okay, for plasma local is very similar to your phospholipid. Okay, the only difference is that the first carbon here, instead of attached to an ester group, okay, is now attached to an ether group. Okay, so and then this ether is then followed by a cis double bond before the arterial side chain. Okay, so that's the different part compared to your C in the second position, which is an ester group as what you see for your triglyceride earlier on, right? Or the common phospholipids. This one came now? Okay. Okay, now let's move on to the sphingolipid. So sphingolipid also has the same casserole backbone as I mentioned earlier on. So this is how it looks like. So the first carbon is still attached to the OH, but the second carbon, the OH is now replaced by an amino group, as I mentioned earlier on. And whereas the third carbon is still an OH, but one of the H of this third carbon is now replaced by a trans double bond, and followed by the hydrocarbon chain, as you can see here. Right? So that's the difference between sphingolipid and the phospholipid and or the triglyceride, because it has an amino group now. So there's an additional amino group. That's what is known as amino alcohol derivative. Okay, and there are a few types of sphingolipid. So generally, the common sphingolipid, the most common one is known as sphingomyelin. So if you look at the sphingomyelin, okay, sphingomyelin has a similar phosphate group attached to one of the oxygen here, the hydroxyl group here. So that is why sphingomyelin sometimes is also known as the sphingophospholipid, because it has a phosphate group attached to one of the hydroxyl group here. Okay. Whereas, of course, you can see here the NH here is now being replaced with or substituted with a polymer residue, which is your hydrocarbon side chain, and then followed by this the unique single sign template that you can see here. Right? So that's sphingomyelin. And sphingomyelin is actually about 10 to 20% of your membrane lipid. Right? And because it has also a phosphate group here, and also followed by all these hydrophobic side chain, so it has a similar charge distribution and conformation as the phospholipids in general. Okay. However, there's also other types of sphingolipid which is very different from sphingomyelin. If you look at the one shown on the center and the right hand side here, bottom right here. So these are known as ceramide. So what is ceramide? Ceramide is when instead of the phosphor group here, right? Instead of this phosphor group here, it is this phosphor group here now is being replaced by sugars. Okay, remember? So the difference between ceramides and sphingolipid is that generally ceramide is also a sphingolipid, but it's different from the usual sphingolipid and sphingomyelin in the sense that the phosphate group in the sphingomyelin is now replaced by sugars. Okay, when it's replaced by sugars, it's known as ceramide, amide, right? A-M-I-D-E, ceramide. Okay. So these sugars, depending on how many sugars are actually attached to the alcohol group. So if it's a oligosaccharides, meaning to say it is a chain of sugars, and then followed by the stearic acid, okay, then it's known as glycoside. Okay, I repeat, if this OH which initially attached to the phosphate is sphingomyelin, right? is replaced by an oligosaccharide, which means a chain of sugars, followed by stearic acid, then it's known as ganglioside. But if it's only attached to any one of these sugar, meaning to say just attached to one monomer of the sugar, either glucose or galactose or whatever, then it is known as saccharoside. Okay, so the difference between saccharoside and ganglioside is that the sugars, the number of sugars are different, right? So for saccharoside, there's only one monomer of sugar, whereas ganglioside will have an oligosaccharide attached to it with a stearic acid. Okay? And follow? Anything to ask? I think I speak actually. Okay, so that's the three different types of lipids that actually contain the fatty acids that we learned in the first slide. So now we're going to move on to the last type of lipid. Right? The last type of lipid, which has a very different structure from the other types of lipid that we learned so far. There's no backbone, there's no backbone or whatever. There's no fatty acid side chain or whatever. But there's this particular structure known as steroid nucleus, right? So have you learned steroid nucleus before? No, right? Okay, so steroid nucleus is a structure with 4 rings, okay? With 4 rings. So how do you come? So you have one ring here, we call it ring A, fused to another ring called ring B, and then followed by another ring C, and then followed by another ring here, ring D. So you notice there's 3 6-member rings fused together, followed by 1 5-member ring. Okay? 3 6-member ring, followed by 1 5-member ring. And the numbering, there's a fixed numbering system we have to follow. So for ring, it usually starts from ring A, number 1 is here, followed by 2, 3, 4, 5, 6, 7, 8, 9, 10, and then down to here, 11, 12, 13, 14, 15, 16, 17. So it's like moving around, whatever. So that's the general steroid structure. So in this case, for a lipid, the lipid is actually a steroid with a C3OH group, meaning to say the third position of the steroid nucleus is now being replaced or substituted with the hydroxyl group. Okay, so that's the uniqueness of sterol. So sterol means what? It's a hotel, right? And we talk about hotel here, we know there's an alcohol inside, right? Can follow? Yeah, so that's why we know that sterol is an alcohol derivative of your steroid. Okay, so that's why you just need to know the position. So the usually is at the 3 position of the steroid nucleus. Okay, and one of the examples of sterol in our body. So I think it's very clear. All of us know what is cholesterol. So cholesterol is actually a type of sterol. As the name suggests itself, you should already call it sterol, right? So based on the name, you should already know cholesterol is a steroid, alcohol. Easy, right? Okay, so what's the importance of cholesterol? You only know the bad parts or bad things about the cholesterol, right? You know that if you too much of cholesterol, it's not good for our health. But do you know that actually cholesterol is actually part of the body? Yeah. So you know that cholesterol is important energy in our body because they actually used to form bowel salts. You know what is bowel salts? Okay, bowel salts is, if you know, right, when you take something fatty, dietary, I mean, if you take it orally, something fatty, when it gets into your stomach or intestine, and the bowel salts will be released, right? The bowel will release the bowel salts into the intestine to actually digest the fatty stuff, right? So that's bowel salts. And of course, cholesterol can also form steroid hormones, which include the glucocorticoid, mineralocorticoid. You will learn about glucocorticoid and mineralocorticoid later on in systems, and you learn about systems, different systems that have the brain or whatever, then you learn all these things as well. Generally, glucocorticoid is for a lot of inflammation action, and all these things. Whereas for mineral corticoid is more for water and solute retention by kidney. Right? And I'm pretty sure you know what's testosterone and estrogen, right? Your sex hormone, which is also made up by your cholesterol. Okay, so that's important, right? Cholesterol is useful in a way, but if it's too much of cholesterol, then you have a problem, a heart problem, etc. Okay, so generally the cholesterol, as you can see, right, the structure is made up of rings and all these hydrocarbon things, right? So generally these are very, very hydrophobic, just like the fatty acids as well, which is why it's classified as lipid. As you remember, to classify other lipid, that biological substance need to be soluble in organic solvent, correct? So that means this is also hydrophobic. Okay. So in that case, how this cholesterol is being transported inside our body, right? So of course it needs to, because our body is made of, there's a lot of water, right? 70% of our body is water. So how is it actually transported in the water environment since it's not soluble in water? So it needs to actually binds to a protein, right? Protein generally are polar. So the protein actually helps to allow this, when it actually binds to the cholesterol, the polarity of the protein helps it to dissolve in the water. So sometimes we call it lipoprotein, which you'll learn in the lipid metabolism later as well. Right? Okay, apart from cholesterol, we also have vitamin D. I'm sure you know what vitamin D is, right? Okay, so vitamin D is also a type of steroid. And this vitamin D, if you look at the structure, of course it doesn't really look like steroids to you, right? But actually, if you look carefully, right, it's actually this, the ring A is still there, the ring C is still there, the ring D is still there, and the other carbon is, hydrocarbon is also there. The only difference is now the ring B has broken apart. Right? The ring B now, one of the bond, one of the 9 and the 10, has been removed, and then it somehow forms something, the double bond, single bond here, as you can see there. Right? So it's actually a derivative of the steroid as well, because you still have the OH here. Right? So what's important of the vitamin D? I'm sure you know that vitamin D is important to promote calcium absorption, and therefore it can increase the calcium in serum, bone, and teeth. So that's why if you go to pharmacy, if you buy calcium supplements, sometimes the calcium supplements they have the vitamin D, right? Because vitamin D can actually increase the absorption of the calcium. Okay? Okay, so of course there are also other lipids which are not part of the our body. I mean it's still part of the body, but what I mean is that it's not part of the membrane component. It's not the lipid layer or whatever, but it still fulfills the lipid characteristics such as enzyme Q10. Alright, you can see here. Enzyme Q10 is like that. Don't have to worry too much. This is just an exposure to you. Vitamin A, E, and K. So whenever we talk about lipid soluble vitamins, right? So there are 4. The way I remember it is nothing based on my old lecturers have taught me that. So it is lipid soluble vitamins A, D, E, K, okay. Water soluble vitamins B, C. Okay, so that's how you remember them. And then we have glycosamides. Again, you'll learn this later as well, especially when you learn about platelets and all those things. You also all learn about this again. So go into learn about this. This is more like an exposure to you. Okay, so that's generally all that I want to share for the types of lipids. Now we're going to move on to the formation of the lipids. But before I move on, is there anything that you want to ask related to the types of